welcome to another episode of Mathcad for Structural Engineers. Today I'm going to be talking about timber and simple design of timber beams. Part of this is to look at the New Zealand code for timber, but also go on to how you create the Mathcad using combo boxes and so forth into creating a standardized timber design. But let's start with the beam design example. This is a solid timber beam taken from the Timber Design Guide by A. Buchanan. So the example tells you to consider a simply supported floor beam spanning 3 meters with uniformly distributed load, supporting floor joists at 450 centers. Let's start with a double component. That's a 240 by 45, and it's machine graded at MSG 8. We've got a span of 3 meters. Our depth is 240 and width is 90 because it's two of them. And it gives us a D over B of 2.66. Our section modulus is simply BD squared upon 6, and our second moment of area is simply BD cubed upon 12. Because we're dealing with timber, we're dealing with rectangular sections, so the equations for the section properties are relatively straightforward. We're going to add permanent loading at 0.84 kilonewtons per meter and imposed loading at 3.15 kilonewtons per meter. So we've taken our load combinations, strength limit state, that's our ultimate limit state. We've got a case of 1.35 times G, and we've also got the combination of 1.2 G plus 1.5 Q. So that's for long-term and medium-term loading. That comes significance into the design of the timber. It's a simply supported beam, so the moment is simply the WL squared upon 8, and the shear is WL over 2. And we've got values for the medium term and the long term. The serviceability limit state, well, we've got combination factors for the short term as 0.7 and 0.4 for the long term. So what are the material properties? Well, taken from our standard NZS 3603, our E value is 8 gigapascals, but we've also got a lower bound in there because in radiata pine strength grade 8, we have a lower bound E value of 5.4, which gives us a mean E value of 6.7. We've got a characteristic bending strength of 14, characteristic shear strength 3.8, and a characteristic bearing strength of 8.9. Our strength reduction factor is 0.8. Now we're just simply putting these in as input parameters. So what's our impact? So what is our beam capacity? Well, we need our K factors, and timber has lots and lots of different K factors. I call them fiddle factors to get around the design of what's a variable material. It behaves differently depending on how you're loading it. So we have a duration of load factor for strength, and that's K1. So the dead load, or long-term loading, is 0.6, and for live loading, it's 0.8. So that's medium-term loading. We've also got a load factor for deflection at K2, and we've got that as 2 because it's internal timber and assumed to be dry. Because of the size of the bearing area, we've got a 1.15 factor for K3. And because you're supporting many components, you've got a K factor of K4 equal to 1.14. So these are all manually put in. Okay, we've got no grid, so the K5 is 1. And the dimension LAY divided by the B is a 5. So our stability factor for bending is 1, taken from clause 2.10. So let's check the bending strength. So your bending capacity at the M here. Well, we put in a factor, a load reduction factor, and then combine all those K factors with the bending strength, and you just multiply it by the section modulus to give you a long-term bending strength of 6.61. In the medium term, you've got a slightly different K1 factor because you're looking at medium-term loading rather than long-term loading. That gives you a bending strength of 8.8. Now the difference between the medium and long term, of course, is creep. So what these load factors are trying to do is allow for creep. That gives us utilization factors for bending of 19% and 73% respectively. Let's check the shear strength. Well, the shear area is just taking us 2/3 of the overall area of the section. We've got a nominal shear strength again, long term and medium term, combining the K factors with the shear strength by the shear area. That gives us long-term shear strengths of 29 and medium shear strength of 39. So our utilization ratios are 6% and 22%. So shear is not usually the issue when you're designing timber beams. Let's check the bearing strength. Now we're assuming a 75mm wide top plate. So therefore our bearing area is 6750 square millimeters. And we apply that bearing area to the bearing strength, combine it with our load factors, and we get a bearing strength, a long term of 33 and a medium term of 44. So utilizations again, 5% and 19%. Let's check the serviceability limit state. Again, it's a simply supported beam, so it's 5 WL to the power 4 divided by 384 EI. So our medium-term deflection is 4.6 millimeters, and our long-term deflection is 6.4. So we're using the mean value for the E for these two. So we have our deflection limit in sagging, and we look at our medium term and decide we want it less than span over 250. That gives us 12 millimeters. Our medium term deflection is less than 12 millimeters, so we're good. Longer term, we're a bit more harsh, so we do an L over 400, and that gives us 7.5 millimeters, which is more than the applied deflection, so we're okay. Okay, so that's a basic timber design example, and you're just using the very basics of Mathcad, not doing anything particularly clever there. Most of the parameters are put in by hand. So let's move to something slightly more complicated. This is a timber beam design, but this time we're selecting from standardized lists. So we've got a range of grades. So here we have a combo box. So it could be grade 8, 10, 12, 15, or different types of timber. These are all given in the code, NZS 3603. So how have I done that? Well, one way to look at it is to edit that. So we cut and paste in our framing grades, our timber grades, as we go down. So that's our first column. You can make that a bit bigger, and you'll notice that it stretches out a bit. So if we go to the right, we've got values in here, and these are for the strength values that we're using. And we've also got E values as well. So all of these parameters are used. We can cut and paste either from the code or from some other online database. And timber sections, let's keep it simple. It's either going to be a double, a single, or a triple. So let's go for a double. And we're using, again, a range from a pull-down list. And again, this is a combo box. To get your combo box, you need to go into your input-output tab, and you will see a basic box there that allows you to put in a combo box, and you fill in the parameters there. So for this sheet, I've already done that several times over. And so our standard, we're cutting and pasting again, either from your tables, your spreadsheets, or from online data sources. And because it's timber, it's rectangular, and most of the parameters are relatively straightforward. So we've got our depth and our width is fairly straightforward. The MM3, that's for the section modulus, the MM4 is for the I value, the MM2 is for the area, and so forth. Now you see I've got some strange units here. Why have I got that? Because the combo box can't handle complicated units, you need to define a set to act as substitutes. That's where we'll come over here and we define our units here. One of them is Newton meters. So that's a Newton multiplied by a meter. Kilonewton meters is basically the same sort of thing, kilonewton times a meter, and ms is 1 meter per second. But we've got more than that here. I was hiding something. If we open this area, I've got my table already made that went into the timber grade. And on my right-hand side, I've put in the units that I'm using. So my MM3 is millimeters cubed. So you're raising it to the 3rd power and you're defining that as a unit. How do you do that? Come to your math tab and you define it as a unit in there. So once you've defined it in a unit, Mathcad recognizes it as a unit and you can use it again and again. And here's an odd one here, kilonewtons per cubic meter. So we put that in as a single variable, but we turn the variable into a unit by assigning it here. So the reason I've done that is to get my combo box to work. And so all of these go with these parameters. So the parameters we've taken from online data sets. And so the Z values given are often times 10 to the 6 millimeters to the cube, for example, and that's why I've given it as so. And similarly, the I values are often times 10 to the 6 millimeters to the 4. And that's what you'll get possibly in your spreadsheet. So hence MM4 is actually standing for 10 to the 6 millimeters to the power 4. Notice up here we've redefined our origin. So by default, the origin, which is what you use in matrices and so forth, but also in combo boxes, because in a combo box, you're effectively setting up a hidden matrix. To make life easier, I set my origin as 1, and then the indexing is a little bit easier to understand. So back to the main body of the calculations. We've put in our data for our standard, our doubles, and our triples. And we can extract from the grade, i.e. timber. So the bending strength FB is taking the 2nd component from the timber. The tension is taking the 5th. The compression strength is taken the 3rd, and so on. And so what you're doing is using this combo box. Let's edit that. And you're marking it out as 1, 2, 3, 4, and so on. So FB timber 2 is the 2nd column in the selected parameter. So if I change it MSG8, let's make it MSG12, all these values then suddenly change as well. So the timber grade, you're just taking it from a list as well. It's the first in the column, MSG12. So you're giving it that label, and that's where you'll use it again. It'll come back. Let's explode that, because underneath our combo boxes, you can use the terms in the combo boxes as basically one-dimensional arrays. And in the combo boxes above, I've made them vertical columns. You can transform that using the transpose function, which comes from the matrices functions down here. So you take your parameter and transpose it, so it takes a column and turns it into a row. So all of these parameters, so I've cheated and put it in the units that we're going to use for each of these occasions. So as it turns out, it's taken that as L, as in liters, as a cubic measurement, and so forth. So we've done the same thing for what I've called standard, double and triple. So it's one piece of timber, this is a double piece, and this is a triple piece. So what do we do? So choice. Now we're creating a thing called choice depending on each of these indices. So the first column of choice is actually you're feeding in whether it's a standard or a double or a triple. So you're indexing it as a first, second, and third row, and so forth. So choice now becomes a matrix. And so we have these fed into that. And if I change my section again, all of these parameters will change. Okay. Now let's hide that again. So our section size that we've picked above now comes through, and that's your choice, column 1. So where have we got that little C from? Well, it's hiding in here. So the parameter C is taken from the type 2, which we've done up here. So our variable called type is coming back to here, double, standard, double or triple. And that means it's going to be type 1, type 2 or type 3. And that means you're picking from that type the catalog. Okay, so you're setting up a matrix as a catalog. And then that's being fed into here. So now choice is a matrix. And so you are picking from the particular row of that matrix. So if you picked a choice of a single, you'd be picking from the first row, picking from a double, you'd be picking the second row, and picking from the third row if you've selected triple. Simples. So from that, you take your B, your D, your Z, your I, all from those matrices. And so you've already pre-programmed in your parameters. The next thing to consider is the K4 value, which is how many elements are you looking at, bearing area factor. So I've got 1 element, 2 elements, and so on. The K4 value will change. Again, it's a combo box. If you edit that, you can look at the second parameter. You've pre-programmed that, in fact, pre-populated the combo box with your choice. So you've got a more or less a pull down, more humane, sensible version of the pull down, which gives you the K4 value. It's a lookup table. And then your bearing length varies, and the K3 value will change depending on the length of the bearing you're using. So if you have a value of a bearing length of 100, your bearing factor, K3, is at 106. So that's all the parameters you've chosen. And then you can move on to the design. Well, by default, your strength reduction factor is 0.8 in this case. And we've got a beam span of 4 meters again, and two lateral restraints. And our tributary width here is 400 millimeters. So you're looking at kind of a joist. And our number of segments, and we've taken the number of restraints plus 1, that gives you 3 segments. So therefore the distance between restraints is your number of segments, your length divided by your number of segments. Okay, so you've derived your bearing length, your area is taken from the length by the width of the timber, and your grid system is actually calculated from all the things above, and the formulas are given in clause 2.9.2 of NZS 3603. Now you could work it out, but this helpfully works it out for you. Similarly, you can work out what the slenderness coefficient is, S1, which then using the formula given in clause 3.2.5. Then you move on from that to the stability factor for bending. And for K8, with the parameters given above, gives you a K8 of 0.97. Now, I've got three different values for K8. One is for dry and one is for wet, and one is depending on how big it is. So you've got a wet value depending on whether the S1 value, the slenderness parameter, is greater than 25. We've simplified it by defining K8 values 4 times and then selecting which K8 value is appropriate. So you have a wet or dry condition. So if you're wet, it changes in using the wet values. And if your S1 value is above 25, you've got different values. So in the end, the K8 value we're using in this case is now 0.99. Shear area, as before, straightforward, and your nominal shear strength calculated as before. Just the K values times the shear strength times the shear area. Bending strength, again, multiplied through by the K values to get your, multiplied by the Z value to get your bending strength. And then the bearing strength, bearing area times the bearing strength times the K3 factor. All of these are given in equations 3.2, 3.4, 3.11 in the code. Okay, it gets more complicated when you start combining these loads because we have load combination factors. Phi S as 0.7, and we've got so for short-term loading. For long-term loading, it's 0 because we're looking at a roof, and for combination factors, we're looking at 0 again because we're looking at a roof. This is given in the New Zealand code 1170.0. If it was a floor, these values would be different. Loading on the beam is 0.65 kPa, and the live load on the beam is 1.5 kPa. So we've got live load on roofs. It's a trafficable roof in this case, and we've got a point load as 1.1 kilonewtons. And the snow we're taking as 0.9. So the wind load on the beam, because it's a roof beam, we've got wind coefficients here of, well, Kp is 1, Kc is 1, Kl as 2. That's a local wind pressure factor. Ka is our area factor for wind, and that's going to be 1 in this case. And we've got our C value for a coefficient of wind pressure as upwards as minus 0.9 and downwards as 0.8. These are all taken from the code NZS 1170.2. So what wind speed are we using? Well, we can predetermine this by using NZS 3604. So that's the code for timber buildings. So again, this is a number combo box. And if we edit the combo box, you can see the values I'm putting in. So for low wind, we give it the code L. And so our basic wind pressure is 0.61. And our serviceability wind pressure is 0.42, and our wind speed is 3.2. The MS there, again, is a specifically designed unit to represent meters per second. We define that above. Okay, so if we change it from medium, these values change. So our wind pressure QU is 0.82 kPa at ultimate limit state, serviceability at 0.56. You combine those together with your combination factors, and we get a wind uplift of 1.476 kPa at ultimate and 0.59 at service. Wind down, that's 1.3 at ultimate, and at serviceability 0.525. So various combinations, we've got our 1.35 dead, and then our dead plus live, and then our 0.9 dead plus wind uplift, and then our 1.2 dead plus wind downwards. And finally our point load, so we've got 1.2 deads plus the 1.5 times the actually applied load, and I've converted that for simplicity into a load per unit length. Okay. How many spans are we dealing? This is a nice little cheat here. because normally we're dealing with simply supported spans for timber, but sometimes you might not be. This is another combo box. If we right mouse click and edit that, it opens it out. And these are the parameters you need depending on how many spans you've got. So have you got one, a simply supported span, 2 or 3 or 4? And so the various parameters we put in here will populate these. So we have a set of coefficients derived depending on what number of spans you've got. So our mid-span moment is going to be 0.07 for a 2-span beam. Now support moment is going to be minus 0.125. The reaction is going to be 1.252. And when you're looking at a point load, you've got another set of parameters to look at as well. So the sagging moment for the point load is going to be the 0.156, and the support moment is going to be 0.188. So we use these coefficients and multiply through by the load times the span squared. We've also got parameters for the deflections. Okay. So our bending moments for the 5 different load cases. So we've got span moments multiplied through the coefficients, and you get 0.39 for the dead only, 1.36, that's dead plus live, and so on. Similarly with support moments, we take the support moment coefficients and multiply through by the load times the span squared. What the utilization comes out as depends upon the loading conditions. So if it's permanent loading, our load factor K1 is going to be 0.6. If I change that to brief, it would jump up to 1. But we're looking at permanent load because we're comparing that with the long-term loading. So our utilization there is 4%. So with the medium term, we're looking at a utilization at 10%. And for short-term loading, our utilization in this case is 2%. So our utilization in the bending moment, you just take the biggest number. In this case, it's 10.5%. You'll notice I've made some of these abs, so I'm taking the absolute value, so eliminating the problems with negative numbers when looking at the maximum. So then we move on to reactions, and we have the same sort of process, multiply the load by the length by the coefficient. And so for our dead load, we've got our 1.75 and so on. We check bearing first, and so that looks at the reactions, and you divide it by the bearing capacity, and we've got a small utilization of 8.9. Look at the shear forces, and again it varies depending on the K1 value, and we get a long-term, medium-term and short-term loading, and you compare that with the long-term, short-term and medium-term capacity in shear. Okay, now let's look at serviceability. And we're going to set our deflection limit as span over 300. You can look through the New Zealand Code 1170.0 for your deflection limits, and those are generally advisory, but I wouldn't ignore them. Take them into account when you're designing buildings, because excess deflection can lead to all sorts of problems. And because we're looking at one element, and if you've got one element, you're going to be using the lower bound value. If you've got multiple elements, you might be using an average value. It also, the deflection varies depending on whether it's dry or wet, or whether it's short term or long term. So if we look at dry conditions, which is basically going to be our medium and long term loading, our K2 value is 2. If we turn that to wet, our K2 value becomes 3. and so you get excess deflection. So hence they're trying to allow for creep in these K2 values. For short-term loading, you're looking at K2 equal to 1, so your deflection is smaller, but usually your limits on short-term deflection are slightly harsher. We then look at vibration, and the code 1170.0 gives some guidelines as to the deflection arising from vibration. It does this by using a unit load. Now, some people use this and some people don't. Now, if we look at the unit load deflection, if it's a single span, we look at the point load of 48. If it's a multiple span, we approximate it to 1/120. Now, I know it's not quite accurate for 3 spans and 4 spans, but it's not far off. And we take that point load deflection and compare it to our parameter, and it's a pretty arbitrary parameter of 1 millimeter. And if it's less than a millimeter under the unit kilonewton load, then we're always good to go. And we finally check the maximum of the deflections divided by our deflection limit, which gives us we're at only 8.7% of our capacity in terms of deflection or serviceability. So to summarize the capacity checks, we're looking at 10%. They're okay. The final note is saying what selection or what section we actually took, which is it's a double section, 240 deep by 45 millimeters wide, and our grade is MSG 12. And that is how you develop your database-driven timber beam design, just for Mathcad.